Hi everybody, welcome back. So this week you're going to be implementing a deep convolutional GAN, or DCGAN for short. These GANs are pretty much like the one you built before on the MNIST dataset, except that the generator and discriminator are built with convolutional networks. So these were first reported on last year, and here's the original paper for DC GANs, and you should absolutely read this. It's not overly technical, and they have a lot of good advice for actually training these things. So be sure to read this at some point while you're working through this. So we're using the Street View house numbers dataset. So this is a bunch of images of addresses, the numbers that are on houses, and it's collected from Google Street View. So these are much more complicated images than what we were using with MNIST. We have, 3 channels now. We have red, green, and blue. These are in color, and they're larger, and it's just more detailed images. And they have, some of these have like a bunch of numbers in them. So since these images are more complex than what we've used before, we need convolutional networks to actually get our generator and discriminator to work well. And this will, show off the power of deep learning and make some really cool images. So basically, the only difference between what you're going to be doing here as compared to what you did in the other GAN lesson is just changing the generator and the discriminator. The rest of the training, like the loss and the optimizers and the inputs, they're all basically exactly the same. It's just the only difference is now our generator is a convolutional network and our discriminator is a convolutional network. So to start out, we just like normal import the data or import our modules, and then we import our data. So this cell here will download and extract the SVHN dataset. So this dataset is actually .mat files, so these are usually used with MATLAB, but SciPy has a function to actually load in these mat files as NumPy arrays. And so we can take those arrays and work with them like we normally would. And here we can see just a small sample of the images that are in the dataset. So these are the real images that we're going to be passing into our discriminator, and this is what the generator is going to learn how to reproduce. So as you might remember from before, our generator is using a tanh output to make these new images, and so that output has a range from -1 to 1. So we need to rescale all of our real images from -1 to 1 also, so that they match when they're going into the discriminator. So here's just some code to do the scaling, and then this is a class that takes our data sets and we'll be able to get our batches from this. So I also built this to create like a test set and a validation set, but we're not really doing any sort of like classification for this network. So we don't really need to use a validation set. This is just for like kind of a general data set class that you can use for the SVHN dataset. Okay, so as before, we have our network inputs, and so we're going to have our inputs for the real images, and so we're just taking the dimensions of the real images, which in this case is 32 by 32 by 3, but I'm just kind of leaving this as a placeholder so you can use whatever size images you want. Then here again, we're using the z vector, so this is the latent vector that's going into our generator. So this is the same as you saw before with the MNIST GAN. Okay, so here's where it gets different, and this is what you'll be implementing. So as before, the input to the generator is, our noise vector z, and then also as before, the output is a tanh layer. So basically the output needs to match the size of our SVHN images, which is 32 by 32, but the output of the tanh is, it ranges from -1 to 1. And we also need to match the depth of these images, right? So our SVHN images have 3 color channels, so they have a depth of 3, so 32 by 32 by 3. So that means that our output layer, which has the tanh activation, also has to be 32 by 32 by 3. So here you see a diagram of the generator that was used in the DCGAN paper. So we just take our z vector, and then we project it to a fully connected layer, and we reshape this fully connected layer to have a size like 4 by 4 with 1024 filters, or the depth is 1024. And then you use transposed convolution to decrease the depth and increase the width and the height. So again, you do this by using a stride of 2 in your transposed convolution. So you'll notice here there aren't any max pooling layers or any of that kind of stuff. No fully connected layers. Like this is a fully connected layer, but past here it's all convolutional layers, and we're doing all the upsampling just using these strides of 2 with our transposed convolutions. So another thing to notice about this is that the final layer here in the DCGAN paper is 64 by 64 by 3, but our images are 32 by 32 by 3. So this is not exactly the same architecture you should be using, but it gives you, at least a hint of, it gives you like an idea for the kind of architecture you should be building for this generator. Okay, so here you are going to build the generator in this function, which we can use later to actually, build the whole thing. But it takes Z, which is our input noise tensor, and then the output dimensions, which is basically like the depth of our output layer. And then again, we're going to use reuse with our variable scope, so we can reuse the generator like you did in the last lesson. And so alpha again is setting our leaky ReLUs, and the training is for the batch normalization layers. So when you're building this, be sure to use leaky ReLUs on these layers, and also batch normalization on all the layers except for this last one. So it's pretty much been found that this just won't work unless you're using batch normalization. And typically the way it works is you do your transposed convolution, and then your batch normalization, and then the activation. Okay, so give it a shot working on this. And as always, if you get stuck or you want to see how I did it, then check out my solution video. Cheers.